Welcome to Carnegie College, and for those of you that haven't attended before, my name is Gary Wagner, one of the principals at Carnegie, and we do these events just about every second Wednesday of every month, so keep an eye out for the invites in the future. Very excited about today's topic, artificial intelligence. For those of you that maybe get Brent's blog, he's constantly sending out information about this quickly evolving technological innovation, and it's really amazing. I'm hoping that he's not going to say investment advisors are going to be replaced by artificial intelligence. We covered that before he spoke, so other than that, so I'd like to introduce Mike Lewicki from Case Western Reserve. Before I do that, just a quick housekeeping item. We always value your feedback. So at the end, on your table, there's a survey. So if you could, please complete that at the end, and not only give us your feedback of today's session, but also if there's any future topics that you would like us to cover. That's how we derive a lot of our presenters. So I appreciate your feedback. I'm not going to make you wait any longer. I'll introduce Mike Lewicki. Thank you.
All right, thank you, everyone. Thanks for the invitation. Am I wired up? Can everyone hear me? So AI is big in the news, and I pulled this from the headlines just yesterday. You know, if you type in any random topic, you might get a few headlines per month, but AI has exploded. And the range of things you see about artificial intelligence is huge. You know, it spans the range from like an optimistic promise. Here's this great technology. How can we take advantage of it? How is it going to like disrupt different markets? But then there's also this underlying concern, apprehension that AI is too disruptive, and you know, it's kind of getting at the essence of things that we might not feel comfortable with. And what I'll try to do today is give you a sense of what AI is and where it came from, and what the technology can do, and try to tone down some of the hype, because there's a lot of hype that is in AI right now. Okay, next one. So the first thing to understand is AI is really many things, and it's been evolving for quite a long time, basically ever since we began to design computers. So AI is robotics, it's computer vision, it's speech recognition. So you're already using a lot of these technologies everywhere, like in your phone. If you've ever talked to your phone, or if you have one of these Alexa devices, that's artificial intelligence. But you're also using it in Google, in natural language processing, when it's interpreting the meaning of what you're trying to say. That's artificial intelligence. It's also in databases and how you represent knowledge, how you query that information, how you compile it to make sense of it, how you relate things of related meaning. That's also artificial intelligence. And maybe the area of AI that's gotten the most press recently is machine learning. And that's the idea that you can have algorithms, and at its fundamental level, AI is just algorithms, but you can have algorithms that learn from data, right? So you're not programming it in the sense of programming a robot to do specific things. You're really letting the machine learn from experience, and kind of like we do. It's very different, as we'll see, but that's a very powerful thing, because you don't have to figure out in advance what needs to be done. You can let the algorithm or the machine figure out what the patterns in the data are, or what the best decisions are, or more recently in the case of Go, you know, what the best move is. And it does this by looking at a lot of data. So one of the reasons it's exploded so much recently is because computers have gotten a lot faster, and our access to data has also exploded. So the combination of those two things has been very ripe for applications of machine learning, and I think that's the main driving force behind why you're seeing all these different companies, because now it's possible to have huge data sets, you know, terabytes of data, whether it's video or stock prices or whatever it is, and then you can have algorithms that try to go through all of that data and find patterns in the same way that we would do, except they're much faster at it, just analogous to a spreadsheet, right? we could have accountants add up all the numbers, but that's slow and tedious. And a spreadsheet does that instantaneously, and it's much more powerful, right? So it's a technology that really amplifies our own abilities. And what I tell my students when I teach artificial intelligence at the university is that if you had to define what artificial intelligence is, it's about representing the world and making rational actions, making rational decisions. So it's those two things, being able to represent some kind of space, whether it's a chessboard or tic-tac-toe or this room. You can represent the room and say the robot has to plan a path to get to the door, right? That's representation and taking action. So the whole field of AI is about how do you solve those two problems? How do you figure out how to represent the world? And then how do you process that data to develop an algorithm that can make optimal decisions? So my whole career has been focused on AI. And when I was an undergraduate in the mid-1980s, I went to Carnegie Mellon because they had the best people in AI. And one of my first experiences was a robot very much like this one. Whoops. Sorry. And I was kind of shocked, because I was thinking, oh, artificial intelligence and robotics, we're going to see some fantastic things. And they had this thing on the sidewalk. And I remember very clearly that it was kind of inching along the sidewalk. You could barely see it move. But the worst part was that they had this piece of orange tape right down the middle. And so it was perceiving the world, but it was too complex to perceive the sidewalk. So they had to put a piece of orange tape, and it could follow the orange tape. And from that moment, I thought, well, we've got a long way to go. And so my own career led me into trying to understand real intelligence, how the brain works, basically. And if you ask me what I do, I would say I'm more of a computational neuroscientist. And what we do is we record from neurons. And my own approach is theoretical. We try to figure out what's the computations that neurons do to enable, say, networks of neurons to be intelligent or to do some computation. So David Marr is a famous computer vision scientist. He founded the field. And he said that an algorithm, and that's really what you're trying to understand, like when we try to understand artificial intelligence or intelligence itself, you're trying to figure out, like, what is the algorithm? What is the algorithm that allows us to learn? How do we process that information? And it doesn't matter whether you're talking about waveforms and sound or images and vision. But he said an algorithm is more likely to be understood by understanding the nature of the problem being solved than by studying properties of the system. And that's the most difficult part about this. When we try to emulate things like what the brain does, or even many animals, it's very hard to figure out what it's doing, right? It'd be like trying to figure out what a computer is doing if all you could do is record from the transistors and the wires. You wouldn't be able to make sense of it, right? So there's a deeper algorithm. And if you go on to the next slide, you'll see that the study of brain function and perception really encompasses a wide range of scientific fields, from perceptual science to neuroscience, but also the theoretical side, which is artificial intelligence and machine learning. Right? So all those things come together, and it's still very much in its infancy. Even though artificial intelligence has had a lot of press and had a lot of technological advances, there's still vast areas that we just don't understand. There's too complex and too mysterious. So what I'll try to do is kind of give you a sense of the scope of this. So let's go on. And if you look at what real intelligence is, so we kind of think that we as human beings are distinct, in the way that we can solve problems and the way that we can understand the world. And intelligence itself began to appear about 70,000 years ago. And the way they can tell is because it was the first time in kind of human history that people did things that were obviously symbolic, right? They carved tools, they made complex like spearheads and things like that. And they had art that was abstract, that represented something different. It wasn't an elephant, it was a little image of an elephant. And that basic ability is what we call intelligence, that you can have something that represents something in the abstract, right? You have an abstract representation that's not as complex as the real thing, but is a representation of that. And that's that first part of the equation that I talked about. Artificial intelligence is representing the world and making decisions about it. So something happened around then that greatly expanded our ability to represent the world. We could solve problems. We could understand complex actions out in the real world. And the idea of artificial intelligence goes way back. And really, you could trace its origins, I think, to Leibniz. And he's one of the inventors of calculus, if you remember from college. And what he said is that he believed that human reasoning, and so that's also part of it, artificial intelligence, could be reduced to systematic computation, right? And so that's, at the time, was a very profound notion, that you could take what we do when we make decisions and make it systematic, right? You could quantify how we do that. And what he said is that when there are disputes among persons, he said, let us just calculate and arrive at the best decision, whatever that is. And that really embodies what artificial intelligence is trying to do. When you have information, how do you make the best decision given the information you have? And that whole field has really been developing since that time. To develop the mathematics, develop things like probability theory. And Laplace, who originated Bayesian probabilities, that's the calculus of optimal reasoning. Right? So that is the origin of artificial intelligence. How to take information and make optimal decisions. And he said that probability theory is just common sense reduced to calculation. And then you could go on, and George Boole invented Boolean logic, a systematization of Aristotelian logic, and that led to computers, right? And so really computers were the start of artificial intelligence because they were the first machines that we built that could make complex decisions. At first it's just arithmetic, right? But when we begin to represent information, we could represent much more complex things. And if once they realized that this was possible with computers, then the mind gets going, right? We can imagine all kinds of things, and there was a hype in the 1940s, just like there is now, that, we have computers, it won't be long before, we'll be able to understand things in ways we've never understood before. And Alan Turing, whom I'm sure you've heard of, proposed a test. How would you know if something was intelligence? And the basic idea that he had is that if you interacted with it, like he realized playing chess, that because at the time he had proposed an algorithm to play chess, right? And chess is a systematic series of moves, and you can write that down in a computer program. And he said, well, how would you know if you're playing a human or a machine, a computer? And he said, well, if you can't tell, it must be actually intelligent. And so he had this Turing test, and this is how he proposed it. And he said, he quoted Shakespeare, and he said, how would you, in the first line of the sonnet, it says, shall I compare thee to a summer's day? And he goes, would not a spring day do as well? And the computer says it wouldn't scan, and scan, means the meter of the poetry. And the interrogator goes, well, how about a winter's day? That would scan. And the computer says, yes, but nobody would want to be compared to a winter's day. And it goes on, and so this was the imagined as intelligence. And I don't know if I would pass this test, but he imagined that, computers, really, there was no limit. They could understand the world. Like, here's a very complex representation of the world. Understanding analogy, and winter and summer, and all these basic facts we take for granted. But he said it should be possible, and that was in the 1940s. And they've made progress. So if you go to the next slide, here's sort of the best attempt. And this is Eugene Goostman. And if you read it, it's kind of like a snarky 13-year-old. It's not really intelligence, because there's no evidence that he's actually representing the world. It's kind of canned responses. What makes you ask me this? Sound like you couldn't choose a right answer for yourself. And so it's generating kind of language, but is there any evidence that it's intelligent? And this did fool some people. They have a contest every year. And if you look at this, it looks very much like natural language. But then you have to ask the question, is it really intelligence? Does it fit that definition of representing the world and making decisions about it? Next slide. So representing the world and taking actions. And so you could characterize that as perception, cognition, and action. All right? And if you go on, this can mean a lot of different things. And so this is Claude Shannon, who is the father of information theory, which made the modern digital age possible. And he was also very interested in this problem. And he built was probably the first artificial intelligent agent, which was this little mouse that could solve a maze. And you could configure this maze in a number of different ways just by putting it in different slots. And if you look underneath, which is in the next slide, it's really just a complex electronic circuit. But it fits that definition. It's representing the world, which in this case is just where is the paths of the maze, and making decisions. Does it know that it's in a dead end, and what does it do when it hits that dead end? And so this expanded, and so this is Alan Newell and Herbert Simon, who are two of the founders of artificial intelligence, and they took this much further because computers became more powerful. And so they worked on chess. They also developed what they call the general problem solver, and it could actually prove mathematical theorems. And that's another example of representing the world. But the world in that case is really these mathematical spaces of, here's some logical statement. How do you prove that this related statement is also true? And you can characterize that with an algorithm. You can set up the space. It can do a search through all the possible implications of that. And they showed that they could prove many of the theorems in Russell and Whitehead's Principia Mathematica. Right? So that was really the first example of where they showed that a computer program could do intelligent things. In this case, what a mathematician was doing. In the same way that computers could also add numbers and calculate logarithms and all this stuff. But here it was something that we really took to mean intelligence, right? Proving a theorem. And this went on, and they were also making grand predictions back then in the 1950s that, in 10 years, no human will be able to beat a computer at chess, right? Because they could just see where it was going. But another theme in this, which I'd like to emphasize, is that the whole history of artificial intelligence and understanding the brain has been an appreciation for just how complex our own perception and our own cognition is. The brain is vastly more complex than we can understand, and what we can do right now is really just beginning to scratch the surface. So Garry Kasparov, who is one of the all-time great grandmasters, he says computers really think very differently than humans. And Deep Blue, which is the first computer program to beat a grandmaster, Garry Kasparov, did 200 million calculations per second. And that's not the way he thinks. When he thinks about chess, he says it's only 1% calculation, thinking about the moves that are going ahead, and 99% of it is what he called understanding, like an understanding of the game. And I think that's very important to understand when you look at artificial intelligence, because it does it in very different ways. It's really, in many ways, doing it by brute force. Because computers are so fast, it can analyze vastly more positions than any human ever could. But it doesn't do it in the same way. Real intelligence is much smarter. They're experienced. They understand, they can create their own mental models, ways to represent that world of chess and make intelligent decisions about it. So I think we've even got along, even though computers can beat humans in chess, they're not doing it in the same way at all. And that's true for most of the things in artificial intelligence. So let's go to the next slide and look at ways that this is implemented. So when we talk about representation, we could represent a chessboard, we can represent a maze, we could also represent text. We can represent an object or a room or sounds or a whole visual scene. And then when we use an algorithm, what we're doing is we're taking that data and finding the best move, or say the shortest path, or parsing it in some way to extract meaning, and all kinds of other things. And in all of these things, you're also doing rational behavior, and that's another important aspect. So you're representing the world, but you're making a rational decision. And so in all artificial intelligence algorithms, there's some definition of what we mean by rational. And usually it's in the point of view of optimality. So in chess, it's what's the best move? Out of all the possible moves, can you choose the one that's most likely to lead to a win, or maybe some intermediate goal? And you could also be, like say the shortest path. Among all possible paths, your algorithm is trying to find the best path, or you're trying to maximize, say, the expected income in some series of business decisions. So it's all based on optimality, and you might already be familiar if you've studied, say, operations research or optimization or things like that. And so artificial intelligence is really just taking those algorithms in optimization or operations research or computer science, but applying them to vastly more amounts of data. And the history of this, it starts with very simple things. The general problem solver, like we talked about, but developing languages and computer programs that allow us to do this. And also, it goes way back, neural networks. You heard about deep neural networks in the news a lot these days, but those really had their origins in the 1950s in terms of trying to understand how to model the brain and trying to understand, does the brain do computations differently than we do in machines? And now we know a lot more about that, and we know that the brain really computes very differently, and we haven't really even understood how the brain computes. We can just emulate some of it in a computer. And then in the 1970s, it was very much about expert systems. You have lots of information, and you try and quantify expert knowledge. What would an expert do in this situation? And that worked to a point, but it ran up against limitations. And this is where modern advances have gone beyond what they could do back then, because expert systems had no flexibility, right? All the information that the computer program had was what came from experts, sitting down, interviewing them, like for a doctor. If you saw this chart, what would the next procedure you recommend? And they try to characterize this, but it's inflexible because it can't learn from data. And what's different today is that there's vastly more information available. Like you can look through medical records, and now there are algorithms that can look, say, at all the records available for some type of cancer. And it can actually outperform some physicians, right? Because it's using vastly more information. That doesn't mean it's the only thing you would want doing that, but it's a powerful tool, right? Because if you had a doctor who could devote their whole time to looking at all those records and coming up with the optimal decision, that's what they would do. But you can do it much more efficiently with an artificial intelligence program. And so now we can go in almost any direction. And this is why it's so promising as a technology, because anytime you have a large amount of data, you can apply these algorithms and say, well, what would the best decision would be? How would I synthesize all of this information and arrive at some outcome? And so you're seeing examples of this. So Google, when you type a search term in Google, that's artificial intelligence, collecting all of the web pages and making relationships among them. Another example is language translation, right? You're taking information, you're able to use vast amounts of data about different languages and how to form translations between one language and another. Another example is self-driving cars, and that's just starting to get started. And this is also about representing the world, whether it's through a laser scanner or some kind of vision, but you have to encode the world out there and make decisions about it. Another example you've seen is Watson, and Watson has been getting a lot of press lately, and that's also about a vast amount of information and be able to access that information in an intelligent way. And on our phones, we have speech recognition is ubiquitous now. It doesn't work as well maybe as we want it, but it's a start, right? And this is the kind of thing that can be a very useful tool. So computers might look very different in the future. Next slide. So another one that is kind of interesting is that there's this tension, I think, in artificial intelligence. When you look at some of these things, sometimes the reaction is you get uncomfortable because, well, is this going to be too disruptive? Will people be just put out of work? And the history of technology is kind of mixed, but it can also be amplified, right? You can amplify your own abilities. So if you're a designer, for example, you might design a chair by hand, but what would it mean if an artificial intelligence program designed a chair? Well, the way you set up a problem is you give it constraints and you say, well, the seat has to be this high, it has to hold this much weight, and you have some kind of model of the wood in the chair and what the structural system can support, and you just let it vary the design, right? You search through this large space to optimize those constraints and those goals. And so what you get is 18 less material and much stronger, and a chair that looks very different, which is on the next slide. The bone chair. And so this is something that comes out of an algorithm. So this, in some sense, is the optimal chair. You might look at that and think, well, That's weird, you know. And why does it look so much like bone? Well, maybe bone is optimal. I don't know. But it's an example of a tool, all right? That you're using a tool in a very different way to amplify what you're already doing, all right? To search through a large design space. Next slide. So in the next part of the talk, I want to try to give you a sense of what artificial intelligence does not do and why some things are really hard. And so this is the intelligence that we don't see. And David Marr, I'll quote from again, wrote a book in 1982 that was basically founded the field of computer vision. And what he said in the 1960s, almost no one realized that machine vision was difficult. And it was a situation where there was wild speculation, just like today. And the moment you had cameras, you know, the idea was that, well, we have a camera, pretty soon computers will be able to see. And it's just vastly more complicated than that. And he said the idea that extracting even, say, edges and lines from a picture might be difficult simply did not occur to people who hadn't tried it, right? And to give you a sense of this, look at the next picture. So that's what the computer sees, right? Just little patches. And somehow your algorithm has to put together those patches. And you look at that, and how do you make sense of it? Well, it's part of the scene. It's a log on a beach. And if you see the whole scene, it just happens instantaneously, and you're completely unaware of how it happens. But we spent 50 years as a scientific field trying to understand like this, and I'd say we're not really that close to doing it like we do. We don't understand how it's done. If you go on, I'll see another example. So here's what the back of your eye looked like, the retina. And so you have photoreceptors, and they're packed in, they're sensitive to different colors. And at the center of your vision, which is where we do most of our seeing, it's only about 40 by 40 pixels, and you're moving that around to interpret the world. Right? And you see the whole rest of it too. And what the brain has to do is somehow take the information from all those pixels and make sense of it. So let's try and do that ourselves. So go on to the next slide. And if you just look at one photoreceptor, you know, it's just detecting the amount of light. Well, what does that mean? It's too hard to tell. If you expand out a little bit, you get a little more, right? You can start to see something, but what is it? It's just too hard to tell. And if you keep backing out, go to 10 to 20 and finally 40, you see these images, but you just can't make sense of it. You know, what is that? But that's the problem our brain faces. And if we put these in context, then it might make a little more sense. So that's where the images came from in the whole scene, but you still can't make sense of it. But now watch what happens when you put in the whole scene. That's what it is. And we have no trouble understanding it, but we have no idea how we do this. And if you go on, you can just quickly go through these, and you'll see that in any one of these things, it makes sense. We see images like that, but somehow we're able to put them together in this larger context. And here's another example. Don't go on, because you'll spoil the surprise. So here's a representation of those pixel intensities just made into a height map, right? So this is the information your eye is getting. And if you look at that, I've given this slide to, I don't know, probably a dozen different classes of 80 to 120 students, and no one has guessed it. So here's your chance. Can you tell what that is just by looking at the... Any guesses?
Yeah, landscape.
A landscape.
Dinosaur skin.
Dinosaur skin, not bad. Let's look at what it actually is. Landscape is partially right, actually. It's a bike, and it's a bike leaning on a tree. And this is how you have to start in computer vision, and that's why it's so incredibly difficult. And you think, well, but we have machines that recognize objects, and we have like self-driving cars. How are they doing it? Well, I want to try to give you a little bit of a sense of how that happens. So go on to the next slide. So here's a classic example that goes back to the 1930s. Remember, artificial intelligence is based on standard principles, statistical information processing, optimization, probability theory. And here are irises. And so if you want to classify different irises, one thing you might look at is the length of the petals and the width of the petals. And they vary, right? And some are shorter, some are longer. And you could classify them based on just those two variables, right? And so if you could figure out a way to extract those variables from, say, a picture, then you could classify which iris. And what classification means is just deciding, in this case, is the data, those two variables, on one side of a line or another. And we can talk about the mathematics of how you would decide that. And if you go on to the next slide, we could even have more complex lines, different kinds of decision boundaries. And we can even have curved ones. And really, this is all machine classification systems are doing. They're dividing things in classes. They're given a huge amount of data. And when you have a deep neural network, it's basically a complex line like that in this very high dimensional space. And it's deciding, is it on one side of the line or is it another? Or is it within this cluster or that cluster? And the more complex the network, the more complex your decision boundary can be. And if you go on to this, the dominant paradigm of these object recognition models is that you take a set of features that you extract from an image, and then you map them into some space where you can decide, is it on one side of the line or another side of the line? It doesn't matter whether it's an ant or a car. So remember what I said remember Gary Kasparov, that he said that computers play chess very differently from humans. And he said they don't understand. They're all doing all this brute force calculation. And this is another example of that. You're doing all this calculation to calculate these features. You have this huge neural network that is encoding that complex calculation of whether it's on one side of the boundary or another boundary, but it doesn't really understand what's there. It doesn't understand, say, that the ant is on a finger or that the car is sitting on the ground. It's not that level of understanding. It's just simply a categorization. And so the next slide shows you can do a lot of things this way. Once you have this tool, it's not like it doesn't do anything. You can still classify faces, right? And if you go on, you can still do self-driving cars. And so this is a frame from a video of Mobileye, which used to be the autonomous vision system of Tesla. And you can see what it's doing. It's also doing a classification, right? And if you look at that scene, there's some things that it gets right, and there's some things that it misses, all right? It's not classifying everything. It's looking for cars, and it's trying to label them and say a car is here. And it can estimate through its sensors about how far away it is. And it can even estimate the volume. But it's not getting like the sidewalk or the posts or any kind of understanding. And that there's a pedestrian right on the sidewalk. It doesn't know in some sense that the pedestrian is there. And there was a kind of provocative review of the autopilot system recently by a robotics expert, a woman who knows what she's talking about, and they went out and tested it. And so if you know how the technology works, you know where to look and to see what its limits are. And she said it gets about 30% of cars right. And that might be enough to drive more safely than we do. So in some sense, that's all that really matters. But her concern was it never seemed to recognize bicycles. And so that was very worrying. If it can't see the bicycle or it can't understand the world, how is it going to make rational decisions? How is it going to avoid those problems? And obviously they're trying to improve it, but there's this risk. And the important thing to understand is that it works very differently from what we do. And there was this story, I remember, many of my colleagues are in self-driving cars, and they were testing an early version of Google's self-driving car. And they went through this, it was doing great, getting on and off the highway, following in lanes, following behind cars and all this stuff. And they went into this town, and it knew the speed limits, so they program all that in, and it can figure out the sign. And it knew the speed limit was 25 miles per hour. And so it's going into town, following the speed limit exactly. But then there was the school bus, and kids flooded the sidewalk, right? And the engineers were in a near panic because it realized in that situation you do not want to go the speed limit, right? And so they had to take over very quickly and slow way down because they understood what was going on in the scene. You had a lot of kids, and you don't know what a kid is going to do, and there's a whole bunch of them. So these technologies have limits, and you have to be very aware of what it is, and it's very different from what we do. Next slide. So here's another example, and this is illustrating context. What is that? You probably can't tell, because you don't have the context. And what makes vision hard is, I can put a frame around it. Doesn't help, right? And I can even take that same pattern, or if you put it in the context, obviously it's a person on the street. Well, what told you it was a person on the street? It's not the features. It's the surround context. But then how do you interpret that? And one of my old colleagues at Carnegie Mellon is Takeo Kanade. He was for a long time the chair of the robotics department. And he had this story that, he drew this simple picture of two lines, which is a road, and then like a squarish thing, which is a building. And he goes, how do you know that's a road? And the answer was, well, because that's a building. Well, how do you know that's a building? Well, because that's a road there. And so it's just very little information, but it's this kind of circular information that we don't really know how to do yet. And if you take the exact same pattern, flip it on its side, it becomes something very different, all because of the context. So this is the hype cycle, right? And all technologies go through something like this. And you have to figure out, well, where is this technology? And I think parts of AI probably are mature enough that they can be applied. They'll be much more efficient at many things, and that will be very good. But there's also a lot of science fiction. People speculating that, just like for cars, we're going to have planes fly. Why can't cars fly, right? And we just don't see that today. And it's the same thing through AI. When Watson is presented as like this person, that's hype, because it's not. And you can easily carry it too far. And I wanted to close by talking a little bit about the brain. And so I spent my whole career basically trying to understand how the brain works. And I can tell you that we have no idea. And it's so complex that we can't even really get started. We know roughly what areas are involved in, say, vision or speech, but how it does it is still very much a mystery. And I'm also a father, and this is my son Phillip when he was 3.5, which is a long time ago now. And when you watch a child growing up, especially when you study cognition and artificial intelligence and all this, you realize just how very different we are. And I remember this conversation at the table. He said, I'm going to eat my milk. And I heard him say that many times. I decided, usually I try not to do anything. I'm kind of the hands-off parent. And I said, well, Phillip, you drink your milk. And then this is the phase where he's always asking why. And I think, well, should I answer this question? And so I said, well, okay, I'll answer it, because milk is a liquid. And I think that's the first time he ever heard the word liquid. But yet he had the concept already in there. His representation of the world included an understanding of things that were liquid. And so right away he goes, is juice a liquid? I said, yeah. Is water a liquid? Yeah, that's a liquid too. Right? And so this is a kind of learning that we just don't really understand. And then he comes to this conclusion, you don't eat milk, you only drink it. I said, yeah, that's right. And I thought, that's amazing. All right, I will open the floor for questions. Thank you. Yes?
Where are the practical applications that are really pushing through that you think represent advances in AI?
The advances. So the question was, what are the practical applications that are really, I guess, areas of advances in AI? Right? And I think probably the biggest one is computer vision, because now you can really have a program that can recognize objects in the world, and you can do a lot with that. And that's a technology that we just haven't had. Speech recognition is another example of that. And if you've interacted at all with them, you realize they definitely have limitations. But being able to do it 90% is still very useful. And I don't really know how long it will take to get the last 10%, or even to start to understand it the way we do. But given the past history, it'll take a long time. Yeah.
Do they have computers that you can speak English and a computer will come back and speak that other person's language very fast, like simultaneously?
They do, actually, yeah. The Google Translate will do this, and Apple just didn't, huh?
Question?
Oh, sorry, the question was, do they have computers where you can speak in one language, and it will sort of speak out a different language and wherever you happen to be? And they're pretty good at this. And Apple just announced this feature on their next version of the operating system where it does exactly that. And it's an example of this 30-year-old technology of language translation, but also voice synthesis. And it's a very interesting area. So that has a lot of applications.
Converted, is the translation good? Like if somebody was speaking Lithuanian to me, could I understand that robot speaking English to me?
That's a very good question. That's the right question to ask. And this is an example of, does it understand the world in the way we do? And there's a famous example of translating Russian to English, or English to Russian, where you say, the spirit is strong, but the flesh is weak. And that got translated as the vodka is strong, but the meat is rotten. And so it doesn't quite understand. And the simplest kind of translation is like word for word, but that doesn't work very well. And people who work in this area have tried very hard to overcome that. But I think it'll be a very long time before computers have kind of the understanding, the experiential knowledge that we draw on for even simple language. So it'll sound like someone who's translating from a dictionary and knows basic grammar. So it's not going to be translating Shakespeare.
Have you witnessed a robot where you leave it to clean a room and it'll vacuum okay for you? Have you ever seen that? I only heard about it.
Well, they have a lot of robot cleaning back rooms, so maybe it's apparently a big area, people. But I've never used one personally. I've never really felt like it replaced my effort of vacuum. I don't know. Maybe some of you have one of those.
There's computer modeling, which, as I understand, you can put in some information and it'll predict what happens further down the road. And I don't understand how you can do that, because it would be an exponential function. You get faster.
That's exactly right.
And it balloons out.
That's right.
And how can it know anything? It's in the field, it needs more information. How do you do it?
That's a very insightful question. The exact same problem happens in chess. When you look out, there's just an exponential number of possibilities. Every move you make, there's like 20-some different possibilities. And that's why they have to do 200 million moves per second, to basically search through them all. But you can be more intelligent. And the way that AlphaGo, for example, you've heard about that, the first computer program beat the world Go champion. And that's even more of this exponential expansion. But the way they could do it is by having a good model of the space. And they could basically discount a lot of these branches and only focus on the ones that made sense. And this is exactly what chess players, grandmasters, do. They understand where they have to focus their attention. So they analyze vastly fewer moves. And also in just general intelligent behavior, you have an understanding of the way the world works. And you understand that there's only a few realistic possibilities. All right, so you explore those first. But it's the understanding that's the hard part. Yeah.
Two questions on Watson. In Cleveland, how close are we to Watson helping us with medical records in Cleveland? I understand there's some things going on. And the other thing, on the quiz show, when Watson was competing against humans, how did Watson do, and any explanation?
Well, for the most part, Watson crushed them. And did anybody watch that show? If you've seen Jeopardy, those guys just know a vast amount of information. But of course, with a computer, you can store a vast amount more of information. And the remarkable thing was they could look up things very quickly. And of course, Watson can do it faster than anyone. And it knows more than, because they had all basically just loaded databases after databases. What was interesting about it, though, was the mistakes it made. Like, there were some very simple questions that a child could answer, but it got wrong. And it's the way it was doing it. You can answer, like the way they would program in books, they would program in all the main characters, right? But you can't really program in like the plot line or something like that, right? The understanding of what the novel means, or even all kinds of common sense situations. And so there were some things that it answered, and the answers were just bizarre. It belied the limits of its understanding of the world. So it does very well with facts and things that it can look up, but any kind of real world understanding, common sense, is still out of its reach.
Also, how about with the memory loss as we get older? Any studies showing how Watson can help us not lose memory?
Well, that's a good, yeah. Well, this kind of gets into neuroscience, right? So what does memory mean? And so my own field, I think that's where that knowledge would come from. And why what is memory in the first place? And we know something about that, but why does it kind of deteriorate as we get older? Or is it a medical condition? Can it be corrected? We don't really know, I think. And it's possible that artificial intelligence will help us with that because it really augments our ability to process data, right? So if you can look through, say, 100,000 MRIs or 100,000 things, you just can't do that as a researcher, right? So it becomes more of a powerful analysis tool. And in that sense, it might lead to a better understanding of the patterns and structure that is there in the brain. And that could in turn lead to helping us stave off the effects of age.
What about garbled speech?
Garbled speech?
Yes.
Yeah, so that's a similar kind of thing. You know, how do we form language? How do we articulate different sounds? And why does that change as we get older? Or even just learning language is another very interesting question. Kids seem to be absorbed language.
Well, if someone speaks on the computer in garbled speech, will the computer come back with the correct answer, although you said it didn't before?
Oh, yeah. Well, that's actually an interesting, it brings up an interesting flaw in some of these, which is, remember what I said when I talked about that line, the classification line, and it's a decision boundary. And for the computer, all that matters whether it's on one side of the line or another side of the line. And you can have an outlier in data, and you would look at it and you would say it makes no sense. But for the computer, well, it's on that side of the line, so it's going to call it that class. And they've shown that if you take a modern classification system that's, say, classifying animals or something like that, you can tweak the data. So the example they had was an orangutan and a panda. And you can tweak the orangutan just slightly in the noise, and you look at it and say, well, yeah, it's an orangutan. But the computer classifies it as a panda. And it's 100% sure that it's a panda, even though it's obviously not. So the idea of inputting garbage, right, is I think one area where computers lack an understanding because the structure of the way that they're making the decision. It's just about which side of the line is on. It's not about understanding the whole structure. Yeah.
Does that recognizing speech, for example, on my iPhone, Siri does not understand me. Most on the telephone, most voice recognition systems do not. Once in a while, I'll hit one that is pretty good at it, but I think that points out the difference in the ability of humans.
That's right.
To recognize versus the machine recognize, because although a few people may have problems understanding me, by and large I'm understood by humans.
Yeah, and that's a very good point. That it's another example how we understand speech very differently from machines. And we're much more general. So there's two areas where we can't really emulate in speech recognition yet. One is understanding speech in a complex acoustic environment. Like if you've ever tried these things, if two people talk at once, forget it, right? It just can't recognize anything. Or if you're in like a restaurant situation or a driving car, the speech recognition accuracy plummets. But another one that relates more to your case is that the way these algorithms are designed or developed is by training on large sets of data. And so if they train on, say, American speech, but it's tested on someone speaking with an accent, or like your voice, it just has never heard that before, right? And so it can't generalize. And the basic problem in all these approaches is how do you generalize? How do you generalize from a small number of examples to an unlimited number of examples? And this is an example of that. So Phillip, you didn't have to train him on what a liquid was. You didn't have to say, well, orange juice is a liquid, milk is a liquid, and so on. He understood that already, right? And speech recognition is also like that. You don't have to train, we kind of develop that automatically. And sometimes people have a little trouble with an accent, but by and large, people can adjust to it, all right? And so that's part of our own adaptability. Yeah.
What's the best way to explain the term algorithm to someone who doesn't?
To explain algorithm to someone?
Yeah.
Well, we've all learned algorithms since, what, second or third grade? So if you understand multiplication, you know that there's an algorithm, right? You start with the last digit, and you multiply those, and you do the carry. That's an algorithm, right? And so it's an algorithm that allows you to compute the product of two numbers is. It can be any two numbers, it doesn't matter. And that's very different from knowledge. We could do multiplication by storing it on a table. You know, we learn a multiplication table, 8 times 9, and you just memorize it. But that doesn't work for large numbers, so you have to have an algorithm. And so the basic difference is algorithms can take any input and compute an output. But memory, just storage like in a database, that's all fixed. It doesn't generalize. So algorithms allow us to generalize. And so all of these examples I've talked are examples of algorithms, just another form of multiplication, or an algorithm to find the shortest path, or an algorithm to sort numbers, or sort names, or something like that. They're all systematic ways of processing the data. And in the case of object recognition and speech recognition, they're just a lot more complicated.
So it's a set of instructions.
Set of instructions, right? And it's also, sometimes it's the feedback loop, right? Where you have a goal, and you're trying one way, you say, is it closer to the goal or not? You know, is it better or worse? And you're kind of doing this large search through a space to find the best answer. So sometimes it's not systematic, but often it is.
So I read that Google's machine learning-based voice recognition now can recognize better than the average human. So you're talking about all the bad part, or the reasons that AI hasn't caught up. But it doesn't, it just has to be better than humans in its particular thing to be effective, right? You know, like cars, it's never going to be perfect, but if Teslas start driving better than humans and only half as many people get killed,
yeah,
it's effective.
Exactly. Yeah, and I think that's kind of a challenge for our society, right? Because we'll focus on the accidents, but it's the things we don't see, like all the people who avoided an accident because there was something that was always paying attention, or you know, a system that was never drunk. You know, all those lives saved. And I think the way Tesla is going about it is smart, right? They're collecting all this data, and so they can tell if the self-driving system were not active, would have had caused an accident. And so they'll be able to point and say, well, look, it's safer, right? And that's all it needs to be, because there's a lot of car accidents. And you know, we might, like in, I don't know if you've heard of the one accident where the person driving was too trusting of the system, and apparently he was watching a DVD, and this semi pulled across the road, and the system didn't see it because the semi was white and the bridge was gray, and the car just went full speed right under the semi. Right? So it was a horrible accident. But it's a limitation of the system. And it'll be challenging, I think, because you put your finger on what the issue is.
What about, like, so one of the things we're talking about is, you talked about at the beginning how the amount of data that we have in general has exploded. Our ability to process that data has exploded, which is what this whole AI thing about. And then there's structured data and unstructured data. Now we have the ability to, computers can now see. It used to be a bunch of zeros and ones that you put into a computer that gets crunched. Now it can actually look and say that that's a planet, that's Earth. It can see cats and dogs and knows what those are, and it's actually absorbing unstructured data. Do you think that's a big deal and kind of next?
I think that's a very active area of research. Yeah, that's always the issue of how do you represent the data or the information. And there's a lot of data that like say speech. It's just an audio waveform. It's really about how do you get at the underlying structure. We know that the words are in there somewhere, or somebody's inflection or their accent is in there somewhere in the audio waveform, but the question is how do you pull it out? Or you look at a scene, I know that that's a table and I know that things are on it, but how do you pull that information out in a general way? And that's still very much a challenge. And you can point to any area where there's a huge amount of data, and the data itself, you can put it in, but can you find the underlying patterns? And I think often that's what people are most interested, the underlying structure.
Do you have any thoughts on the internet? Like a lot of people have heard the term Internet of Things in here probably. Do you have any thoughts on that and how artificial intelligence is accelerating that or affecting that?
Well, the Internet of Things is, basically allowing, it's sort of an extension of our appliances, where they get more and more kind of intelligence, right? But then what if they could communicate? And that would open up a lot of possibilities. And anytime you add capability, you need some intelligence, just for it to be easy to interact with, to behave in a way that makes sense to us. So anytime there's behavior, there's opportunity for machine learning and artificial intelligence. So I think it'll be a big part of it. Yeah.
Talk to us a bit more about the research you and others are doing on actual brain understanding of its work.
Okay, well, I should say that's a vast field. So there's more areas of brain science and neuroscience that I could even name. But I can talk a bit about my own efforts, and that's been on the perceptual side of it. What I'm trying to understand is when sounds go into the ear or vision goes into the eye, what happens to it? What are the principles of information processing? And if we understood that, we would understood how, not only how it's done, but why it's that way in the first place. And so part of the problem is coding the information. It's like when light goes in your eye, your optic nerve carries the information to your brain. And we don't really understand the code that's in that optic nerve, right? So, the very first thing is still mysterious. And when the light hits your photoreceptors in the back of your retina, there's a lot of processing that goes on, and we don't really understand what that processing is doing. And so the science, that actually reminds me of something else I wanted to say. That's the science of it. And the science is to understand you have something you're comparing against, right? So we take the brain as being the ground truth. And if you can understand it, you should be able to predict from optimal algorithms why it's doing what it does and get insight into how it's doing. And a useful way to think about artificial intelligence more generally is it a science or is it a technology? And it's a bit of both. And a friend of mine came up with this analogy. And we put a man on the moon in the 1960s, right? And at that point, it was a technological problem. We knew that if we put enough resources behind that effort, we could get to the moon. It was technologically possible. But if you go back, say, to 1900, it wouldn't matter how much money you put behind it. It just wasn't technologically possible because there were so many fundamental scientific issues that hadn't been solved. And AI is very much like that. There are many scientific issues that we simply don't understand, and I've tried to illustrate some of them here. But that doesn't mean that it's not useful, but there's still a long way to go. Yeah.
So is there a resource that you think does a good job of kind of predicting that future, given there's a lot of, it's not just a computational problem? Because I think a lot of the reason there's so much hype right now is you can't predict, no one can predict the future.
Yeah.
And some people are saying, hey, this stuff is 20 years, 10, 20 years away, and other people are saying, gee, it could be 50, it could be 75, it could be 100.
That's the challenge, isn't it? I think what's difficult, if you talk to the people who are creating the technology, they understand the complexity of the problem. They understand that, well, we've only solved a small piece of it, and there's a lot that we don't understand. But just like the self-driving car, it doesn't have to be perfect to be valuable, right? And so I think what the scientists and researchers can't say is how this is going to be valuable, right? When you put it out in the market and start solving problems with it, the simplest things can kind of take on their own life, right? And become something, wow, I never thought we could do that. And that's a technological problem. We have a basic technology, how can we apply it? And I think there's a lot of creative exploration out there in the marketplace right now. They're not doing the research, but they're taking tools that have been developed and trying to find ways to apply them. And I'm sure I don't know if we can predict that future.
Is there one that you feel kind of reflects your own personal beliefs on things, though, that you can point us to?
I don't think I could name one thing. There are so many things. I mentioned computer vision, speech recognition. Personally, I think the biggest opportunity for this is something that would help us make better decisions. You know, how to make better decisions in the face of uncertainty. And that's something we don't do naturally at all, but artificial intelligence is based on the mathematical solution to that problem. So it's a solution that exists, but just like the spreadsheet at some point didn't exist, there's some tool that will amplify our decision-making ability that hasn't been invented.
And it just predicts odds, basically. It's saying, you know, 90% chance that this is the right thing. You can't predict the future, but you know, the Tesla self-driving car and senses a car coming this way. It figures out, takes a whole bunch of pattern recognition skills and says, this is probably what's happening here, but it's not going to be.
Yeah, well, I think one way to sort through the hype is to look at it and say, do they have a working example? Is the example impressive? Does it do something that hasn't been done before? And Tesla is an example of that, right? Because they've taken the self-driving car to levels no one thought was possible, really, except maybe for a few optimists. But you know, they've demonstrated their technology. And a lot of what you read out there, I think, is speculation. You know, it's saying, oh, look, we could do this, but they don't really have a working example. And sometimes it's just, I think, writing articles to get views or something like that. You know, it's more like science fiction, because they're just engaging in like optimistic futurism or something like that. Oh, what over here?
Can you, and I hope I didn't miss this, I got it, came here late. Can you generalize about what kinds of professions might be obsoleted?
Yeah, well, I had this debate. So at CASE, the Inamori Center for Ethics hosted this debate on artificial intelligence. And we debated the ethics of it. And one of the points that was brought up is it's basically about the economic model. It's the economics of disruption. And like any other technology, you know, technology can either amplify ability so that a person can do more, but if the technology replaces someone, then it becomes a threat, at least to that, you know, the people who made a living doing that. And it could be right now that it's happening so fast that it's too disruptive. And I think it would be a mistake. There's this tension, I think, that exists where they think that, for example, in doctors, you know, since the system could make better decisions than a doctor, well, let's just have the system make the decisions. But I think that's a mistake, because you have to pay attention to what the system doesn't know. And we are still vastly better at understanding like real-world issues and all these other bits of information that aren't in the database, you know, this hidden information. And so I think it's much better to think about it as an amplifying or enabling technology. So if you're in the business of making decisions and processing data, it makes you better. It makes you make more accurate decisions. It allows you to process more data. And then fields like, say, medicine, doctors could, you know, make better decisions, decide how to get to the root cause of someone's problem much more quickly, much more effectively. You could, you know, if you're an insurance company, you could apply artificial intelligence to minimizing the number of procedures that would need to be done. You know, all kinds of things that could be applied. But there's, you know, there's things on the horizon that would be very disruptive, like, say, truck drivers. Does the truck driver need to be there? And, you know, there'd be a lot of people out of work if it happens too quickly. Or security guards. You know, if you can just have a computer just, you know, watch, you know, kind of more vigilantly than any security guard could, do you need the security guard? And then what happens then? So these are challenging issues that we face. You know, it can be very good, but it's also very disruptive.
Isn't it an inherent problem using a digital computer to simulate brains that the brain is for in an analog world?
A very good question. And you've hit upon the paradigms of computing. Like, so we compute using the von Neumann architecture that's based on Boolean logic, right?
And that's 70 years old or so.
Right. And one thing I well know is that neurons are just vastly different. in ways that we don't even understand. So one thing that makes me think that we'll never really be able to get there, and just like we have jets, right? We have powerful flying machines, but they're nothing like a bird, or a bumblebee or a butterfly. They just do it in very different ways. And well, why can't we fly like a butterfly? And it comes down to that nature is just incredibly efficient at what it does. If you look, the brain uses 15 watts of energy, right? And that's less than most of your laptops, let alone Google's huge bank of computers, right? So it's vastly more efficient at what it does, and it's also vastly more specialized. And so you look at computer graphics, right? So once we understood the principles of graphics, we could begin to make specialized machines to do that computation very efficiently. And so now we have GPUs, graphical processing units, that can do those computations very efficiently. Whether we're scrolling or making artificial worlds or games or whatever. And the architecture of the brain is even more specialized. It computes using neurons and electrical signals and molecules, and that's very difficult to emulate. And I think we don't even really understand what those principles are yet. So there's possibility that there's a whole computing paradigm out there that can use tiny amounts of energy, that computes in very different ways, and we don't even really know how to program it yet.
It's a whole different concept.
It's a whole different concept, yeah.
Neuromorphic computing?
Yeah, actually when I was at Caltech, so I went to Caltech for graduate school, and Carver Mead was there, and he was one of the pioneers of neuromorphic engineering. And it was about finding different paradigms of computing. And the quote in his book, which I often use in my class, is that it's his belief that the paradigms of computing of biological systems are vastly more efficient and effective than those used in machines. And they do some amazing things, just making use of transistors. And we haven't even yet begun to build things that kind of emulate the neurons or brains, because we don't have the science, right? It's a scientific problem, not a technological problem.
Transistor, they're working in sub-threshold.
That's right, yeah.
So it's not the digital world.
It's not, yeah, so transistors are usually, think of binary, but if you lower the current, they become analog, and then you can do a lot different kinds of computations. And so they actually have a cochlea that normally you have a digital computer, it takes a lot of energy just to process the sound, like if you have a hearing aid, it takes a lot of battery. But if you do it in a different computing paradigm, your battery would last for years, because it's so much more efficient, and the architecture of the computation is specialized for doing exactly that computation. And that's a very good point.
Who's making these computer chips or whatever it is that are making? Who's making the thing that, say, in your chess game, if you had two of those artificial intelligence, which one would win?
So the question is, if you had two artificial intelligence systems playing each other, which one would win? And I guess that's something like if you had two grandmasters playing each other, which one would win? And they often end in a draw. And that's probably what would happen, my guess, is because my son's been really into chess, and he said it's really about not making mistakes. And what makes computers so good is they don't make mistakes. And so if you had two computers playing each other, most likely they would play to a draw.
The thing that's made this socially possible at this time, I presume, or I see, is the ability to process huge amounts of data in a very short time. That's the basis of the whole work.
I would say that, yeah, and the algorithms. So there's been development in the algorithms themselves. The question is, how do you process all of that information? And that required a lot of research to kind of find ways to do it efficiently, to ways to do it effectively, and that's still very much ongoing. There's a lot of exploration. So it's not very much an unsolved problem, but there are some solutions. But this explosion in computing power and storage power has really enabled a lot of things. That's right.
Is there still a difficulty in learning what is still quantifiable in a sense?
Oh, very much, yeah. So what's the phrase that not everything that counts can be counted, right? And that's very true, because when you represent the world, it's by definition a simpler version of the world, right? And you can't represent the world in all its detail. And the question is, what do you pick? And in things like computer vision, there are things that you don't even know how to represent. Like, I can tell that that is plastic and that's aluminum. How do I know that? You know, you could give me some, you know, you could make the table wet, and I said, well, it's wet there. How do I know that? You can't read that off. It's implicit in the way, the structure of the data. And so there's so many things like that, you know, it might be in the database implicitly, but you have no access to it.
So it's an issue of human beings having more qualitative understanding of the world that a machine just can't ever attain?
Yeah, well, I don't know if it can't ever attain it, but maybe go back to that school bus situation, right? So the question is can machines, are they limited in terms of what they can represent about the world? And by and large, that's true because they have to be programmed, right? And so in the case of the Tesla autopilot, they could program in the speed limit. They could sort of write algorithms to recognize the sign and read off the number, or know which road it's on, things like that. But they never thought about a school bus that lets out a bunch of children, right? How do you understand that situation? So that's real world experience. And there's been efforts in the history of AI to kind of program in all that real world experience. So, you know, in the 70s, there was this big effort to basically take all this knowledge and like put it in a database somehow. But you can't. Like if I ask you to tell me what a parallel line is, how would you describe it? Things like that are very hard. Or how do you know when someone is sick from their voice? You understand it. Or a better one is, like, how do you tell male from female? You know, everybody can do it, but can you say what it is that allows you to do it? You know, and all that is kind of implicit knowledge. It's very difficult to kind of put in your database. Yeah. So maybe I'm the one kind of emceeing this, or...
Well, thank you very much, and thank you for everybody. All the great questions. You've been very generous with your time. I don't know if you have a few more minutes. If anybody has anything.
Oh, sure. I'd be happy to.
Thank you very much.
Get into the nitty-gritty.
The only question I have, I'm glad to hear we're not going to be obsolete. So, is there any good place to go for resources to just kind of keep abreast of?
Ooh. That's tricky. Depends how technical you want to get. You might, like, the technical journals like MIT Technology Review. Good, comprehensive articles about the technology, and they're much more immune to the hype side of it. Or IEEE Spectrum is another place where you see things like that. Vox is pretty good with technology, I found, but it's hard. I think there's a lot of people who are fascinated by it, but you know, they write about something they don't understand, and so it's hard to get very deep information about it. So I can't really give you a definitive source.
Thank you. Unless there's any other questions, again, if you could fill out the surveys, and thank you for coming.
Thank you. Great crowd.